Hey guys, Mr. Goochee here. I'm ready to walk through the section 1.3 notes that we covered today, which was formulas and equations. Minimizing my screen right here. Okay, guys, ready? Let's go. What I did earlier was I ran through an example of a chemical reaction where I added pure sodium metal to a beaker of water. And we saw a violent reaction occur where the sodium metal reacted with the water to make hydrogen gas and sodium hydroxide. I'm not going to show you that video now because I posted it somewhere else in the notes and in the daily roundup. So if you want to go watch that reaction, if you didn't catch it in class, go catch it there. Okay. Now, how would a scientist describe that chemical reaction? Because it's a bit of a mouthful to always have to say sodium metal combined with water reacted to form sodium hydroxide and hydrogen gas. It's a mouthful, all right? What chemists do is they have a specific language to describe chemical reactions using symbols and formulas, okay? It's the exact same way how in a math class, when you turn a word problem into an equation before you solve it. Okay, so you get a word problem in math, you got to convert it into the language of math, an equation, in order to solve it. Chemistry has equations too. So, for example, here's how I would describe that reaction that I performed in my sample video. All right, sodium reacts with water to produce hydrogen gas and sodium hydroxide. But here it is written as a chemical equation. All right, here we go. Two sodiums plus two waters, H2Os, yields an H2 and two NaOHs. Now, you're not exactly sure what those twos in front mean or what that arrow means or why there's a little two there, but we'll get to that later. This itself is a sample of the kind of chemical equations that we're going to be writing. And we'll start with the basics, all right? Every element can't be mentioned by name in an equation. You have to represent it with its own symbol. And its symbol is just one or two letters that stand in for that element. And you can find all these two-letter symbols, one or two-letter symbols, on the periodic table, okay? For these one or two-letter symbols, the first letter is always uppercase. The second letter is always lowercase if there is one. And every symbol makes sense, maybe just not in English. So, for example, the symbol for carbon is just C, all right? The symbol for bismuth is Bi, all right? But the symbol for gold is Au. Just minimize that even more. The symbol for gold is Au. Now, why is gold Au? Why is it not G or Go? Because gold in Latin is aurum, Au RUM, I believe. All right, it's where the symbol of the term aura comes from. Same Latin root as like a glow or like a sunrise. All right, which clearly represents gold a little bit. Every scientist around the world uses the exact same periodic table with the exact symbols. So every symbol on there makes sense. It just might not make sense in English. Okay, so for example, here's a map of Europe, and here's what they call element number 11, sodium. In half of Europe, it's called some variation of sodium, sodio. In the other half of the nations, it's called some variation of natrium or natrio or natri in Russia, okay? Or natriju in Belarus, all right? So in that case, they win this. All right. So we give it the symbol Na because that's what half of the world calls it. Okay. Here's the periodic table, and you can see all the symbols for all the elements are listed here. And what's that kind of light blue highlight? That just represents the elements that we are going to be working with this year. So if you're going to become familiar with any of the elements, it should be these elements right here, the ones highlighted in blue. Okay, now we figured out that elements are represented by symbols. When you want to represent a formula for a compound, the rules are also pretty simple. Okay, what you do is you just put in the symbols for all the elements that are in the compound. All right, so every element that the compound contains, you put in the symbol. So, for example, water. It's got two hydrogens and an oxygen. So you start by just saying, oh, it's got hydrogens and oxygens. And then you put in a subscript. Okay, now a subscript notes how many of each atom type are present. Okay, so even though it's cut off in the bottom of the screen here, because water has two hydrogen atoms in it, we would say that it is H2 And then since there's just one oxygen, O, okay? Subscripts come after and below each element, and this is important. If an if a compound only has one type of atom in it, like it only has one oxygen or one carbon or whatever, you don't give it a subscript. It gets no subscript. No subscript doesn't mean zero elements. If this water had zero oxygens, then why would we either even bother putting an O in there in the first place? No, this is if there's only one atom, you don't give it a subscript. It's the same way how, again, in math class, if the answer is X, you could say X, you could say 1X, but why say 1X when just X will do, right? In algebra class, if there's only one of a thing, you often don't put a multiplier in front. Well, the same thing for subscripts. It's a multiplier. So if there's only one of a thing, you don't put the multiplier below it, all right? By the way, when it comes time to making subscripts, in Google Docs, for example, you're going to want to go to the Format tab. You're going to highlight the number you want to turn to a subscript, go to Format, Text, and then you'll see the option there to turn something into a subscript. I'll post a separate video on that later. Okay, so chemical formulas, again, it's real simple. So here's glucose. Here's a glucose molecule. So what's the formula for this going to be? Well, count up the carbons. 1, 2, 3, 4, 5, 6. There's 6 carbons. Count up the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. And how many oxygens? 6 oxygens. So what's the formula of this glucose? It is C6H12O6. Now, if by some chance you don't have access to subscripts, like if you're typing it in a browser or in a Pear Deck and they don't let you do subscripts, if you just write it down, and it's kind of cut off there. Yeah, here we go. If you just write down C6H12O6 like that, that'll be okay. But if you can write subscripts, like if you're writing it by hand or using Google Docs or something similar, make sure you make those numbers tiny and lower. Okay, so here's a propane molecule. What's the formula? Well, if the blacks are carbon and the whites are hydrogen, then we got 1, 2, 3 carbons. So carbon is C, C3, and 8 hydrogens. So hydrogen is H, so H8. The formula for this substance, which is propane, the thing that you put in your tank and your grill, is C3H8. Here's another one. Here's ethanol, aka drinking alcohol. Okay, what is the formula for this substance? Well, let's see here. There's 2 carbons, so C2. There is 6 white hydrogens, so H6, and there's 1 red oxygen, so O, not O1, although it's technically not wrong, just O. So C2H6O is the formula. Okay. Now, if you were to just Google ethanol, you might get something slightly different. It might be C2H5OH. All right. So I'll tell if you Googled something and didn't try and figure it out on yourself. There's a reason why it's slightly different depending on who you're asking, but just do the simple counting up of atoms right now and listing them out. Okay. Cool. Now, once you have your formulas for your reactants and your products, you're going to want to write a chemical equation. It's real simple, okay? You just put the formulas for all of the reactants, the starting stuff, on the left. So sodium, the symbol is Na, all right? That was one of the things. The other thing we added was water, all right? Those are the things we started with. So Na and H2O, those are the reactants, okay? And what did we end with? We ended with hydrogen gas and sodium hydroxide. So those are the products. Their formulas go on the right. If you have more than one of a reactant or product, you got to put a plus sign in between them so that I know it's Na and H2O, 2 separate things. Whereas if there wasn't a plus sign, it would just look like NaH2O, and I'd be confused because I had no idea what that is. That's not a real thing. Not a real thing. All right, so put a plus in between if there's more than one product or reactant present. And lastly, you should have a yield arrow, that little arrow there that points from the reactants that you start with to the products that you finish with. Okay, so that yield arrow right there needs to be in this equation. So it's very simple. All right, you list all the things you start with on one side, and then an arrow pointing to the substances that you end with. It's pretty self-explanatory. Don't overcomplicate it. Okay, you're going to be fine. And we'll learn little details about why these formulas are the way they are later. But just know that this is how the language goes. Okay, now there's a few other symbols that get involved in here sometimes. Like, for example, sometimes it's important that we list out what state of matter something is in. Like if one of the reactants is solid water versus liquid water, sometimes that matters. Usually it doesn't. But when it does matter, we have symbols. Okay. So if something is a solid, then we put a little S after it in parentheses. If something is a liquid, we put a little L after it in parentheses. Something's a gas, we put a little G after it in parentheses. Again, we're not going to deal with this often, so don't bother putting these in unless I ask you to. But just a few more symbols. All right. Now, I want to kind of change gears here real quick and talk about something else, an important idea in chemistry, and that has to do with the concept of mass. Now, mass is the amount of physical material that something is made of. For example, this right here, this gentleman playing the guitar is Canadian astronaut Chris Hadfield. He's a really cool guy, okay? He plays guitar on Earth, he plays guitar in space, dude plays guitar under the water, all right? What a neat dude, okay? Now, we would measure how much physical stuff Chris Hadfield is made of, and that's called his mass. And we'd measure it in grams or kilograms. All right. Now, the cool thing about mass is that mass is something that does not change based on where you're located. All right. So, for example, when Chris Hadfield goes into space, his weight changes, but weight is just gravity pulling on your body. Okay. Your body is still the same. Chris Hadfield is still the same amount of stuff that he's made of here. All right. His mass does not change, even though his weight does. And when Chris Hadfield is playing guitar underwater, he's kind of floating there. So he feels a little bit weightless. He is buoyant, but his mass has not changed. All right. If Chris Hadfield weighed like 78 kilograms here, then he probably weighs 78-ish kilograms here and 78 kilograms here. Only way Chris Hadfield can like change his mass is if he eats a lot, goes to the bathroom, maybe pumps some iron, puts on some mass. Okay. So mass does not change based on where you are. All right. And this is important because one of the most important ideas in chemistry is this idea, the law of conservation of mass. Mass is never created or destroyed. You only can shift the pieces around and rearrange it. And chemistry this means that in the large scale, if you start with 10 grams of a reactant, like if you add up, the sodium that Mr. Goochee added was 3 grams and the water was 7 grams, that's 10 grams of reactants. I have to end with 10 grams of product. All right. I can't create or destroy material in a chemical reaction. The mass is conserved. It means it stays the same. At the atomic scale, that means that if I start with a certain number of atoms of a certain type in a chemical reaction, I am going to end with that same number of atoms of their same type at the end of the reaction. We don't create, destroy, or change atoms from one type to another in a chemical reaction. All that happens is we switch their bonds and how they are connected. All right, so this is the law of conservation of mass. This is one of the key ideas in chemistry. Like right up there is like atomic theory, maybe number one, and then a close second is the law of conservation of mass. Okay, so here, for example, is a video, a time lapse of logs being burned. I'm just going to skip forward here. All right. I don't know if you can hear the music. I can. All right. But what we see here is like over time as we burn the log, it seems as though the logs are shrinking. They're getting smaller. Like, oh, well, clearly we're burning the log. The mass is being destroyed. But that's not what's happening, okay? Because mass is never created or destroyed. What's happening in this video is simply the atoms of the log are being changed. And maybe they change into something that we can't see or detect as easily, but they're still there, okay? Where log stuff go? Mr. Goochee, you're saying stuff isn't created or destroyed, then where does the log stuff go? Well, I'll tell you. It turns into gas. it floats away. When you burn a log, it turns into mostly carbon dioxide, which is a gas, and it turns into water, which, being it's so hot, disappears as steam. So you don't see either of those things. They just disappear into the air. But if you could collect all that stuff, put it in a container, and find a way to take the mass of all the water and carbon dioxide and ash that's left over would exactly equal the mass of the log that you started with. All right. Okay. The log and the oxygen, because you need oxygen to burn this log as well. Okay. So, what this means that in chemistry, all right, we add multipliers in front of the substances in a chemical equation. Okay. For example, here is that sodium and water reaction. Let's take a look here. Take a look at the sodium and water reaction. Okay, we start out with sodium. So just let's take a single sodium atom. Okay, I represent it as purple, and an H2O, which is made up of an oxygen and two hydrogens. Okay, great. Those react and they produce hydrogen gas and sodium hydroxide. Now, I don't know, but can you notice that something's a little bit off here? All right. Something doesn't quite match up. What doesn't match up is that there are two hydrogen atoms over here, but there are three hydrogen atoms over on this side. This violates the law of conservation of math. Hydrogen can't just appear from anywhere. All right. Hydrogen just can't randomly show up. So what we got here is an unbalanced equation. So let me show you how I'd balance this real quick. Okay, I'm going to jump out of this presentation. All right, cool. Now, let's take a look here. One sodium and one sodium. So there's the same number of sodiums on each side. We haven't created or destroyed any sodiums in this reaction. But there's two hydrogens over here and three over here. So what we'd have to do is we'd have to get more hydrogens on this side. So what I'm going to do is I'm going to say, okay, instead of one water, let's say that we take in two waters. Okay. Now, unfortunately, this unbalances us further. Okay. We have two oxygens over here and only one oxygen over here. So we gotta double this up. All right. We gotta double up this stuff right here. So I'm gonna double up this. Okay. But now we got a problem where now we got two purple sodium atoms on this side and only one on this side. So I'm going to double this up over here. All right. And I'm just going back and forth. It's like, oh no, we messed up the number of hydrogens. Now I got to put some over here. Oh, that messed up the oxygens. We're going to learn about this. But the point is that the reason why you have these numbers in front is because now, let's see here, we have two sodiums over here and two sodium atoms over here. So the number of sodiums are the same. We have 1, 2, 3, 4 hydrogens over here on the reactant side, and 1, 2, 3, 4 hydrogens on the product side. We have two oxygens on the reactant side. We have two oxygens on the product side. This is balanced. This chemical equation now conserves mass. We have not created or destroyed any atoms. So we had two sodiums. We're going to put a 2 in front. Okay. We had two, I'll make this a little smaller. We had two water molecules here, so I'm going to put a 2 in front here. We have one H2 molecule, and we have two sodium hydroxide, so I'm going to put a 2 right there. So these numbers in front just represent how many of each molecule or atom type we would have to put in this reaction in order to start and end with the same number of each atom. Okay. And so that is called balancing a chemical equation. That is making sure that we have not just the type of ingredients and the type of products, but how much of each we need to put in and expect to get out so that we conserve mass. Okay. So there we go, guys. That's the video. I hope you enjoyed it. All right. Later, folks.